All right, so at this point, after looking at the fundamental of finding antiderivatives, then let's now go ahead and set forward and head ourselves into doing some more basic rules on taking antiderivatives. And along the way, I'm going to introduce a couple more examples, the basic kind of examples that combine the basic rules that I'm about to introduce here. But most fundamentally that you have learned earlier, that the only rule, the most fundamental rule, that's what I meant, we've learned so far is the power rule that I've been leaving on my other board. I've been leaving that on my board. But now to get the best out of our later rules and getting to our next examples, then I'm going to completely clear out all the boards here. Okay, so now as far as the rules, at this point, let me now get on the other board, and we're going to do a few. So I'm going to use the other board for doing some deriving work. Okay, so let's quickly take a look at, so we have a function, how about 5, and I want to find the antiderivative of that function. So 5 is the function, and the antiderivative here, so I mean, we've just, once again, at this point, and when anyone doing these antiderivative problem, think as closely as possible to the work that we're doing a derivative, and then think in the reverse way. So if our derivative is a 5, if our derivative of a function is 5, then what function would that be? So and keep recalling for yourself that, reminding yourself that question I brought up earlier, that what function has a 5 as its derivative. So if we keep thinking along that way, then it makes sense that now that the answer has to be 5x. Because when we're taking derivative of 5x, and that's pretty much the only explanation I have, and that's pretty much the only way we can check for whether we've gotten our correct final answer. So taking the derivative of 5x gives me the answer is 5. So now that tells me that 5x is a good candidate for being a derivative of this function 5 right here. But now, since we have already learned more than just that, and so in this case here, the actual general derivative for this function 5 is 5x plus c right here. So now viewers to this video, and as well as my students, can start thinking ahead of time a little bit. Now I'm putting up, how about 3? So antiderivative of 3. Treating 3 as a derivative, and let's find the antiderivative of 3. So you can spend a little bit of time thinking, but now I see this. You see, it's a different problem. It's a different problem, admittedly, but in the end, it has the very same concept with this other one we've done earlier. The function that we start out taking the antiderivative here is a constant function. The function that we're starting out to take the antiderivative here it wasn't. The function f of x equals 5. Here it is now f of x equals 3. And so along that way, so it looks like my answer is going to be having a 3x, because see, again, we can quickly check. Taking the derivative of 3x gives me 3. That's the constant. But now this is only a derivative, or in what we have learned previously, this is the main derivative right here. So in that way, the general derivative must be adding that constant c right here. All right, so 2 problems we have done so far. Our final antiderivatives turn into a linear function when it was originally, before taking antiderivative, a constant function. Okay, and so, and we can also have something like this. How about a negative 1,000? So find the antiderivative. So recall for yourself, at this point, everything we learn is that this symbol and the dx is one symbol, indicating taking the antiderivative, indicating to take the antiderivative. And so our function here is essentially a constant function, negative 1,000 as a constant function. And so after the 2 examples and the 2 experiences we have done here, I mean, after the experience of the 2 examples we have done, very previously, then the answer here should be quickly negative 1000 x plus c. All right, so now 3 problems are just good enough for me to bring up a generality as a rule, to a basic rule to recognize, and then from now on, anytime we see this kind of setup, it will click immediately. So now I'm introducing basic rules. So the first basic rules, and of course the first of the basic rules outside of the fundamental power rule that we have learned after we already mastered the power rule. So here the first basic rule here is that anytime we're taking antiderivative, that's why this is one symbol, and our function is simply a constant c, just a constant c right here. And so then, and on my board here, it's a little hard to tell, but I purposely use a lowercase constant c right here. And there's a reason why I mentioned this. But so now in that way, how I'm seeing, then, or how about, let me switch this. I feel a little unsafe for this. So how about the constant here? Let's just call that the constant a right here, just a constant a. So anytime we're taking the antiderivative on a constant function, namely a, then our final antiderivative is ax plus constant c. So this c here is a capital C. It's just a tradition. But it's a constant term being added to your main antiderivative here. But so this is one basic rule. All right. And so now I'm going to immediately head out to the next rule that I would like to introduce. And actually the next rule I'm about to introduce here is still really rule number 1 right here, but I want to call that, how about a special case? So how about, let me correct my way of saying it, but the next rule is really just the special case of this current rule number 1 right here. So I have to introduce this as a special case simply because the way how I start out teaching, and specifically I teach how to use this symbol at this point, is only I want my viewers, my students, to see this symbol, the 2 pieces of the symbols here, as one particular symbol to indicate finding the antiderivative. So in that case, there's one special case here, when sometimes you see something like this. Other instructors who might have a completely different approach with me to explain about the symbols may not need to explain immediately what that is. But in my case, since I only introduced this symbol as an instruction to find antiderivative, then this actually is a problem, even though it seems nothing here. That's the part I want to mention right here. So a lot of times you will see something like this, just simply the symbol and the dx itself. Okay, and everything looks a little scary in terms of there's nothing indicated here. But so what's special about this is, now I need to point out, this is really, that's 1 dx. Okay, and so in my style of teaching this, of approaching antiderivative, and later on to get to the kind of problem where we're dealing with integrals, then later on when I formally introduce what an integral is, then you will understand, you will make the connection of why and how, magically from having a completely something absent here and all of a sudden it turns into a 1. You will get that explanation there when we arrive at my later video lessons. Okay, but for now, since I started out teaching using this symbols, that's as one package. But in the special case like this, where there's only the symbols, the symbol, this sign here and that dx coming together, but no particular function indicated, it means the function you're trying to take, the antiderivative, is 1. Okay, and so now from that point, once I have cleared up for my viewers and my students to understand, then the answer can come out easily according to this basic rule number 1 that we've learned, because this is rule number 1. The 1 here is constant, is a constant. So it's just x plus c is your final answer. Okay, and so this is the special case and that I was talking about earlier. All right, so now let's move over to my other board. And now I'm going to immediately head out to a completely different rule. And let's now call that rule 2. And then once I introduce that rule, I am going to show a quick little example to go along with that to see how useful that is. Okay? And this is not example 4 actually, because we have done example 3 earlier, but the one right after this rule is not going to be example 4. So for now, rule number 2, among our basic rules for taking antiderivatives, then so now the rule now says if we're attempting to find the antiderivative on a function, and the function itself is in the form of having a constant coefficient multiplied to that constant. So of course, having a constant coefficient multiplied with a function is another function. So basically, the whole c times f of x is our function that we mainly need to find the antiderivative. But now the rule I'm about to introduce allows us to do the following. This rule tells me that, hey, anytime that we're trying to find the antiderivative on a function where we recognize it mainly has a constant coefficient like that, then we can just simply take care of the antiderivative on the individual function without the constant coefficient. And then at the end, once we have found the answer to this antiderivative, then we can just simply multiply the constant coefficient back. And that's what it is for this rule. So now I call it rule number 2. And so now I'm going to immediately bring up a little example. And now this is what I said earlier about it's not example 4 in continuation with example 3 we have done, but this is just only a quick illustration example to illustrate how we can use this little rule. A little rule, but very powerful, surprisingly useful for here. So, little example here. That's why I wouldn't name that, I wouldn't number that. Okay, so we have done, so this is how about 3x squared dx. Okay, 3x squared dx. Okay, so we have seen in our earlier discussion, still in this lesson, that if we're just simply taking the antiderivative of the x squared right here. See, this is something that's so easy for any viewer at this video lesson right now. But now 3x squared, so it's not just x squared, it's not just the plain old power function. Because on something like this, then we have already learned that we can use the power rule here. But now it's not simply just the power function, it has a coefficient in front. And so now the rule we've just learned here says, hey, what we can do here is simply just take care of that antiderivative and then multiply whatever that is for 3. Multiply whatever that antiderivative is with 3. That's all it is. That's how easy it is. And so now we can just, without any worries, go ahead and find the antiderivative on your x squared. So that gives me 1/3 x cubed according to the power rule that we have learned. And then all that there needs to be multiplied with a 3. And that's how we're doing that. And of course, do not forget, add an overall plus c constant at the end. Okay? And so now at this point, the constant coefficient 3 will cancel with the 3 in our denominator here. So our final function now turns out x cubed plus c. So that is our final general antiderivative of the starting function. And what we used here was primarily that rule that handle in the case where our function comes with a constant coefficient. So now from this point on, we know what to do. We know how to handle when our function involves a constant coefficient. Okay, so that would be rule number 2. So now I am going to get back on my other board, and let's look at rule number 3. And so rule number 3 here, I see that as one rule, but many textbooks start out explaining that as 2 separate little sub-rules. How's that? And then eventually we all bring that into one rule. And so this is what it says right here. So a lot of times when you're finding the antiderivative of a function, then your function comes with two terms being added together. That's what I'm trying to say over here. So sometimes the function that you're trying to find the antiderivative comes as a sum of two other terms, and each of the terms now at your mathematical majority here, then each term in a function is of course another term. So basically anytime you are finding the antiderivative on a function that has a multiple term like this, connected by the adding or connected by additions, then this is what the rule says. So this is called the sum rule, okay, because now obviously right in front of us there's a sum to take the antiderivative. So the sum rule says you can individually find the antiderivative for f of x, and whatever that is, you are allowed it to add to the antiderivative of g of x. Okay, and so that's the rule that's famously called the sum rule. Okay, so just like that, two terms or multiple terms, but sometimes the terms may be connected by a subtraction. So for example, I'm talking about something like this. Maybe it's f of x minus g of x, or subtract g of x. Okay, so we could be doing a problem or some part of a problem where we're handling a function of two terms but connected by subtraction. Okay, so now here we call that the subtraction rule. Actually, that's not a good way of saying it. The formal term, difference rule. Sum, and this is difference, because that's there we have a difference of two functions. Okay, so the difference rule. Okay, so now the difference rule say we can simply find the antiderivative, but see, anytime it comes to difference, then we have to be extremely cautious with the order of the difference here. So our term or our little function f of x comes up before the subtraction sign. So that means you're going to have to take the antiderivative of f of x before the subtraction. Okay, and then the rule now says antiderivative of f of x can subtract the antiderivative or can minus, take the difference between these two, the antiderivative with the g of x. Okay, so that's the difference rule. Okay, and so the rule like this. So as I said earlier, any one of these rules, I see that as a sub rule of the bigger rule right here. That so basically the idea now is that mainly the rule that we just learned now in rule number 3 allows us to find the antiderivative term by term in case your function gets long, it contains multiple terms in it. So in that way, let me really finalize rule number 3 right here as one rule. One rule that involves, that explains about the sum and the difference of two terms here. So this rule is generally regarded as sum or difference rule. Okay, and it says that anytime we're taking the antiderivative on a function that's having at least two terms. Okay, and our two terms are either connected by addition or subtraction. Okay, so if our two terms are connected by addition, then the sum rule would kick in and say we can just simply find two separate antiderivatives, one for f of x, one for g of x, and add them up. So if it was if two terms in the beginning functions to take antiderivative were added, then our two antiderivatives will be added. So on the other hand, similarly, if the two terms here in our beginning functions for taking antiderivative is connected by subtraction or being related as a difference here, then their two antiderivatives need to be in a difference. Okay, and so this rule number 3 right here is the more generalized version, and where I so-called the sum and the difference rule, like that. Okay, and so something like this. Let me bring up a quick little example right here. Only a quick little example, and we're still not yet at example number 4. And so Just a little example to demonstrate the idea. All right, so how about x to the fifth plus x cubed minus x squared, okay? Something like this, dx. Now anyone viewing this video of mine will immediately understand the reason why I introduced this rule over here. A very important rule that allows us to find antiderivative for a function where it contains multiple terms like this. So now, according to the sum rule, see, first two terms, and at this point, anyone viewing this video should be well familiar that anytime you're looking at the terms of a function or the order according to the order of operations, then we will always start looking at things from the left to the right. And so, of course, we're not going to have to worry about the powers here because we already have the power rules to handle. So now, as far as the term, then looking from the left to the right, then we produce the following three separate antiderivative problems. I can see x to the fifth as one problem. So I am going to take a separate antiderivative for that one, for that term. I see x cubed here connected with x to the fifth as a sum right here. So I'm going to have to produce a separate antiderivative for x cubed and add that to the other antiderivative that we've had so far. And then the last term here of our original function that we're trying to take antiderivative for, the last term here is an x squared that's connected to the other terms by a subtraction. So now I'm going to subtract the antiderivative of x squared. And that's how I've been saying this rule allows us to find the antiderivative term by term. Okay, and so at this point now we can find the answer quickly and easily. So I'm a little bit running out of space on my writing board here, so I have to write it a little squeezy at the bottom here, and it might look a little hard to read. But first antiderivative gives me 1/6 x to the 6. Okay, middle term and still adding gives me now 1/4 x to the 4th. Okay, according to the power rule that we have already learned. And then the last term here is being subtracted. The last antiderivative is subtracted from the other two terms. So now minus 1/3 x cubed. And don't forget, we don't need the antiderivative symbol here anymore, but we need to do the plus c because that's our final general antiderivative here. Okay, so that's what it is. All right, so now let's get ready to head into example 4, where we can do a combined example. We can do an example that combines all the rules we've learned so far. Okay, so I'm now going to advance to the other board, clear out the board. All right, so let's now look at example 4 here. And we just want to find, okay, we just want to find, so now find what? We just want to find, how about question A here? We want to find the antiderivative of our function being, how about 5 x to the 9th minus 4x to the 6th plus 3. Okay, one function being a polynomial, 3 terms. Okay, so now we're ready to bring in all of our understanding after learning about all the rules here. So immediately, what caught my attention here about this function, which we're trying to find the antiderivative, it has 3 terms, and first 2 terms are connected by the difference, or connected as a difference. And from this second term to the last term, these 2 terms are connected as an addition. Okay, so the sum and the difference rule blended together allows me to do this. It's a 5x to the 9th dx. We can just simply or individually take care of that antiderivative on the first term, and that's what it's meant for. And then minus, and so now antiderivative on individually 4x to the 6th. That's the antiderivative of the middle term. And then here we're going to need to use the sum rule. So the reason I had subtraction here was because of the difference rule to be applied on the first two terms of my my original function. And now moving on from term number 2, the middle term, to the last term, I'm going to add according to the sum rule. So now it's antiderivative of 3. What function gives our final answer being what function has 3 as a derivative? That's what this says right here. All right, so now if we're looking back at this very first term right here, then the function itself, we have already learned how to use the power rule on the antiderivative of x to the 9th. So that should be we should be able to take care of that easily. But now this function x to the 9 is not only x to the 9th, it's a 5 times x to the 9th, meaning we're having a constant coefficient here, constant coefficient 5. So first term we can advance a little further with that. Now the rule number, and I don't even remember the rules anymore. The point now is that we just learn what we learned and we apply right here. Some textbook call that rule number 1, some textbook call that rule number 2, and then it's all over. So I believe that was rule number 2 in according to my order of these rules. So I can pull the constant coefficient, leave it out, or separate it out. I only need to mainly handle the antiderivative of our main power function. Okay, and then so let's do the same way for this thing. This is now going to be the same as 4 times antiderivative on the plane power of x to the 6. And then that's how about I'm going to leave that here for now. So we have carefully applied the rules to treat each of our terms here. And so now we are ready for the final answer. So first term here is a 5 all together with coefficients and all that. So first term here becomes 5 times, so now how about a 1/10 x to the 10th. That's the antiderivative for the first term together with its constant coefficient. Okay, and then the next term here becomes, so minus or subtraction sign is still here, 4 times, now I'm looking at a 1/7 x to the 7 according to the power rule. And then the last one there we have used, we are now going to use rule number 1 here. Okay, and so if I remember the order, how I order my rules correctly. So this should be 3x, okay, that's how easy that is. And then so all of these we can just simply produce one final overall constant plus c. Okay, so we are so close to getting to the final answer here. This is our, this is already the complete point where we had our antiderivative here. However, let's algebraically clean up the terms here a little bit more. All right, so now in my next step here, continuing from the previous step, then quickly as a reminder. So first term, we can cancel the 5 with that 10 in the denominator. And that's pretty much all we can do. So it's going to be a 1/2 times x to the 10th power minus, now, and the 4 times 1/7 here, everything else I can do with that is simply to put that as one fraction. So minus 4/7 x to the 7, and then plus 3x plus c. And that's how we're advancing to our last one. Like that. Okay, so that's how we effectively used our the rules for basic rules for taking antiderivative. Okay, so let me now swing back on the other board, erase out this part A, and let's look at part B of our example. All right, so in that way, in our part B, let me create another one very similar to part A, but it involves a little more challenging powers. And so how about 3 over x minus 2 square root x, okay, and plus e to the x, how about 5e to the x? Okay, and we're having a function like that. All right, so the sum and difference rule first say and allows me to find the antiderivative term by term on the 3 separate terms here. So that means I'm going to produce a 3 over x as one separate antiderivative for the antiderivative for 3 over x. It's one problem, one separate term for our antiderivative. And then the next term of our antiderivative has to be 2 square root of x dx. Okay, so the symbol together here is one symbol, right, for finding the antiderivative. Now plus taking another antiderivative for 5e to the x dx right here. Okay, and so now I have to start explaining a little bit. This 3 right here, the nature of this 3 over x is to be thought of, is to be regarded as 3 times of 1 over x. Okay, so that's what the 3 over x is. So let me write it in a different space right there, so viewers can recognize that a little more. So 3 over x is the same as 3 times 1 over x. So this is our main function, and we have seen throughout our earlier part of this lecture that what would be the antiderivative for 1 over x. And so in that case, this is what I can do. So now after my explanation there, I'm going to erase the quick little notes there. So that means I can pull the 3 as a constant coefficient. And my point of doing that earlier, of writing that as 3 times 1 over x, because I want viewers or my students to recognize that the 3 here in the numerator of this simple fraction is acting as a constant coefficient. And then the other part is just some function that we can recognize. So now that means according to constant coefficient rule, I can pull the 3 out front, and now 1 over x dx. Okay, this one here is recognized easily. I can bring that in front. But now see, after we bringing that 2 out front, the square root x here in our experience we have learned back in some of the earlier example where I purposely brought up those problems where we're having root as expression. Then we learned that square root x can be re-expressed as x to the 1/2 power. So now we have a function that we are well familiar with to handle. And then this expression 5 times e to the x. See, I just said right there, 5 times e to the x. So this 5 right here is another constant coefficient of this whole overall function. And so that means now I can leave the 5 in front, okay, and only need to individually take care of the e to the x function. Okay, all right. So now at this point, first term gives me 3 times the only way we arrive at this final answer is natural log of absolute value x. Okay, so antiderivative of 1 over x is natural log of absolute value x. And then don't forget the constant coefficient 3 in front. Now minus, and allow me to start assuming that viewers have gone through the earlier part of this lesson, and so been fluent with that, and at least some addition and subtraction with the fraction. So now it's 2 times, now my value here is x to the, let me write that a little more carefully. X to the 3/2 power, but multiplied with 1 over 3/2. Okay. And then in the next term, it's just simply 5 times e to the x, because taking antiderivative of e to the x is e to the x. We've just learned in the earlier part of our video lesson here. Okay, and now plus c. So in that way, I am going to move on to the other board. And so now my first term is 3 natural log of absolute value x minus, so 2 times 2/3 x to the 3/2 power, because now again allow me to swing back on the other board. 1 over 3/2 is the same as 2/3. And of course, the final power on that middle term is a it's a 3/2 power. And then in the next step, I am going to multiply these two coefficients together anyway. So plus 5 e to the x plus c. And so the very, very final antiderivative here, and the final general antiderivative, 3 natural log of absolute value x minus 4/3 x to the 3/2 plus 5 e to the x plus c. That's our final answer, which is satisfied by many instructors. Okay, because right here there's still about 50% chance that your instructor doesn't like this expression, and then of course when you're leaving your answer like this, it's not it's the correct answer. It's the final answer already, but it's not simplified. So there are a high percent. I mean, there's a high chance that your instructor will not like this kind of expression here. Okay, and so that's how we got to the final answer here, which everything is very simplified, and any instructor should be feeling pleased about this final answer, this kind of final answer right here. All right, so let me show another example. I mean, another problem in this particular example here. So I'm going to switch to the other board. All right, so actually I should call that a different class of problems here. So let's call it example 5, even though we're all about finding antiderivatives here. Okay, so how about part A of our example? So the function that we're trying to find antiderivative appears to be in a product. Okay, so in a product, x squared plus 1 in product with x plus 5, for example. Okay. And so I pointed it out that the function we're trying to find the antiderivative here, for now, at start, appears to be a product. But now there's a sad news for us. Right after the power rule, I have only introduced the 3 basic rules ever. Is there a rule that will directly handle this product? There sadly isn't. So I have to now make it clear that there are no product rule. I wrote this down earlier in the earlier part of our lecture, but I have to emphasize that again. There are no product rule, meaning there's no rule to directly handle something like this and maintaining it being a product. There's no way of doing that. So there's no direct product rule. And the reason I have to mention this, because taking derivatives, as we have learned prior to entering this lecture right here, has when you're taking a derivative work, there is a product rule. But now when we're taking the antiderivative, there isn't any rule that we call a product rule. So there's no product rule. Okay? Does that mean we're not going to solve the problem? That doesn't mean so. We will find the antiderivative of this, but we need to apply some treatment. So now being in a product like this, then we can FOIL out. And so for now, since we have not learned any advanced techniques, FOILing out is the only way that we can handle the problem. So now I am going to just take some time FOILing it out. And FOILing out is the algebra work. So in any step, you can take 5 steps. You can take only 3 steps, but doesn't matter how long you go, as long as you're still FOILing, you're still going to need to keep the antiderivative symbol here. Okay, and so in that way, now I'm going to spend some time FOILing out. So x squared times x gives me x cubed. X squared times 5 is a 5x squared. Okay, and 1 times x now is a plus x, and 1 times 5 is a 5. So now it turns out that we are having a polynomial of 4 terms, where all these terms are added together. So now we can easily apply the sum rule that we have learned earlier. So we completely bypass the need for the rule to handle this product directly, because there isn't any rule like that. There isn't any rule that can handle a product directly. So we have no choice left rather than just foiling everything out. Okay, and so now, but see, you may break it down to smaller steps, but as long as you're only working on the algebra, then you still need to stick to your antiderivative symbol here. But now the next step I'm about to get into is the actual antiderivative step. So now I'm going to find, and since we're still, allow me to assume that anyone viewing this video is still a beginner to this. So let me move on with the steps carefully. So the next step now is to break it down into terms by terms. So one antiderivative for the x cubed plus another antiderivative on the 5x squared plus another antiderivative for the x term and an antiderivative on the constant term. All right, but now after that point, now we can start picking up the pace a little bit. So in that way, my first term becomes 1/4 x to the 4th. Okay, my middle term, my second term becomes, okay, let me remind anyone viewing the video about the second term is here. Okay, so that now gives me 5 times 1/3 x cubed. Okay, and then the third term on my list is simply going to give me 1/2 x squared, and the last term is a 5x. Okay, so now I'm going to add an overall constant c to our antiderivative, and so now we can clean up the terms a little bit more. So 1/4 x to the 4th plus 5/3 x cubed plus 1/2 x squared plus 5x plus c. Okay, and that is our very ending of the problem right here, which is the final answer to our antiderivative of the original function. All right, and now I'm going to introduce another one that should be worth our attention. All right, so now how about part B of example 5 right here. So how about we want to find an antiderivative for x to the 4th minus x cubed plus 3x. Okay, and then we are dividing by x squared, for example, dx. So yes, I agree. Anyone viewing this video will agree with me as well. This is a quotient. It's a quotient. There's numerator, there's a denominator, but sadly, there is no quotient rule. So just like product rule, there was no product rule. Same here, anytime that we're seeing a quotient, there's no quotient rule. There's no quotient rule. And the intention here is that there isn't any rule that can help us directly handle this antiderivative as in the way it is as a quotient. So, but that does not mean at all that we're going to give up. So, nope. But being a mathematician, one of your quality here is that you won't give up. Okay, there are math problems out there that it takes mathematicians centuries of being as a mystery, but in the end, some of them are going to overcome and discover something new. Okay, so now knowing that we have no quotient rule allowed it, because there isn't any proven quotient rule that worked, and so this is what we can handle that. So we can apply some algebraic treatments again. So notice the good thing about this quotient is that the numerator has only one single term, and so we can take advantage on that. So I am going to do the following. I am going to, according to the algebra property of a quotient, okay, numerator has multiple terms, but denominator has only one term. We can do the following. I'm going to put x to the fourth over x squared as one separate fraction. And then minus x cubed over x squared as one separate fraction. And then 3x over x squared as another separate fraction. Now all of a sudden I turn my function, I turn my starting function into a function that has 3 separate terms. Okay, but now anyone viewing my video here will start clicking immediately that, and we'll see immediately what my intention is and where I'm about to go with this. You see now, if we can just simply simplify each one of these, see, we're still going to find antiderivative because right now it's just the step that we take the algebra treatment. So now x to the fourth cancel with x squared gives me first term in our beginning function here, being the x squared. Okay, minus, yes, just like that, x cubed cancel with x squared gives me x. 3x cancel, the x in my 3x here cancel with x squared gives me plus 3 over x. Now we can, with our limited number of limit laws, I mean basic rules right here, with our limited number of basic rules right here, that's what I meant to say right here, then we are already very able to find the answer to this. Okay, and so, all right, so now the sum and difference rule says we can find one separate antiderivative for the x squared and then subtract the antiderivative on the x term and plus with the antiderivative on the 3 over x term. Okay, and that's how we're going to handle that. And so first term now gives me 1/3 x cubed. Middle term gives me 1/2 x. So the two antiderivatives now appears to be, together they appear to be 1/3 x cubed minus 1/2 x squared. The last term was something that we can bring up the experience we have seen in earlier example. This is the same as 3. This is the same as 3 as a coefficient times a 1 over x. So that means now I can treat that as a constant coefficient 3, but taking the antiderivative of 1 over x is going to give me natural log of absolute value of x. Okay, and so plus c as an overall constant. We have now arrived at our final answer. So at the start of our problem, there was no quotient rule proven for us to handle this problem directly as a quotient, but we applied algebra, some algebra steps, some algebra treatments, and turned our problem into a function, a beginning function of 3 terms, and any one of these is all within our reach. We can all do any of these antiderivatives, and so any of these steps was just an algebraic re-expression of our problem. So definitely we need to carry over, we need to keep carrying over the antiderivative symbol. Okay, and then even when we moved on to the next step where I already applied some basic rules right here, we still gonna have to apply the antiderivative symbols on each one of these the terms. But now when we get to this point right here, these are all answers to antiderivatives, and we no longer need to find to use the antiderivative symbols. Anyone viewing this video might feel it's a waste. I keep repeating these things, but believe me, there will eventually be some students who mistakenly, still leave the antiderivatives here at the very final step. And if you're not my students, if you're my student, maybe I understand you. But if you're viewing this video but learning that for a course with different instructors, you might be in trouble with the way that how you write like that with your instructor. So that's why I'm trying to be as clearly as I can here. Okay, but in the end, this is our final antiderivative for that. Okay, so now let me spend some time erasing the board and bring up example 6 here, which is a completely brand new class of problem, but very fascinating. So now in our example 6 here, and I'm going to have to start writing down some wording here. So how about we're given a function. f of x to equals, let me see what I have in my own creativity here. Some examples I never have to prepare, and some examples I do prepare a little bit. So how about x squared plus 3x minus 5, okay? And so I want to find, so we're given that as a function. Okay. I want to find. So we've been through with this. Most of the time now, yes, we're using this symbols and our function here for indicating finding the antiderivative. But now since I switched to wording mode, so I want to find capital F. And that's what I'm trying to explain right here. So if our function here is notated as a lowercase f, then capital F under our, within what we understand right now is just simply the antiderivative of f of x, the corresponding same letter, the corresponding letter, but capital version, that's antiderivative. So I want to find capital F of x, meaning the antiderivative. That's satisfying. Okay. That's satisfying. How about f of 0 equals 3. Okay. So that's the entire structure, and if you are learning and taking notes at the same time, so write down the way how this problem is worded. It's a very standard way of how the problem is worded, and you will see this problem in a, you know, you will see this problems a lot of times in your work out there. Okay, so now let me move on to the other board. Make some space, and then we're gonna start getting it. And now, one more time, let's look back at the problem. So the problem started out by having a function given to us, x squared plus 3x minus 5 here. So let's now not be too worried about this capital F0 equals 3 right here. Let's not be too worried about that. The main thing here is that we want to find the antiderivative. Okay, we have our function given. We want to first find the antiderivative first. And once we've found an antiderivative, we're going to start taking care of what it means by satisfying this. Okay, so let's take the first step of our journey here. So find the capital F prime. So at this point in our learning, capital F prime can be found by simply, yes, doing the antiderivative work, and that's what it is. And so I prepared a symbol, but I realized I need a little more space. So how about x squared plus 3x plus 5? There's our function originally given. And let's take the antiderivative to arrive at, let's find the antiderivative to arrive at the capital F of x. Okay, so this is the work for us right here. So capital F of x now should be, so you are very welcome and highly likely to do this. Keep rolling back to the videos, to the earlier part of the video, and keep reviewing my examples earlier to get fluent, because here in this problem I'm going to start picking up pace in quite a few elementary steps right here. So for example, I'm not going to be too far beating around the bush with the recalling about the sum and the difference rule. Of course, we're going to have to apply the sum and the difference rules here, and then the power rules need to be, of course, applied here. So I'm going to pick up pace a little bit. First term is going to give me 1/2 x cubed. That's what I meant right there. And this is already the answer, so we don't need to write the symbol for antiderivative. So now taking antiderivative allows me to do term by term. So middle term, I am going to have a 3 times 1/2 x squared, because we separate out the constant coefficient, and we only need to find the antiderivative of the x. And so finding the antiderivative of the x is a 1/2 x squared. That's why I ended up with 3 times 1/2 x squared. And then sum rule again, sum and difference rule again allowed me to find the antiderivative on that constant term, but connected by the subtraction sign. And so here it's going to be 5x. Okay, but now plus c. That's our famous first step in finding any antiderivative. And so now capital F of x is 1/2 x cubed. Actually, I just now realized I've been wrong the whole time since step 2 here. This is supposedly x cubed times 1 cubed times x cubed plus 3/2 x squared and then minus 5x plus c. So there we have found for ourselves the antiderivative. But now this is only, see, recall that in the language, in the terminology that we have already learned, this is only, what we have here is only regarded as, see, what we have here is general antiderivative. That's only the general antiderivative. Okay? And we are stuck with this constant c right here. So let's look at our further requirements of this problem. The further instruction of this problem says we want to find, because recall from my from my earlier explanation that a general antiderivative now is really something that represents an entire family of antiderivatives. There are many members in that family. They can be, whatever that is plus 5. They can be whatever that is minus 1,000. They can be whatever that is plus 1/2. So that's why, like I said, we have one main antiderivative that ends here, but then the plus c makes different members of the entire general antiderivative. And so that's why, in that reason, here's the intention of this problem. When we start looking at the requirements of the problem here, we want to find that particular, and I'm starting to use that word, we want to find that particular antiderivative where it satisfies this requirement. So this is what that whole f0 equal 3 is all about. This is what it says that, see, capital F0 means we're substituting x equals 0 into, if we're substituting x equals 0 into our general antiderivative here, see, substitute x equals 0 in here. Okay, then the overall value equals 3. And so now let me start getting straight into it. F0 on its own, okay, then it's going to give me 1/3 times 0 for cube plus 3/2 times 0 square minus 5 times 0 plus c. You see how I got that right there? I simply substituted 0 into my general antiderivative that I have found. Okay, so that's the general antiderivative. And then over here, I substituted in 0 for x. So that's what capital F of 0 is. And we want the requirement here says all of that here satisfies equal 3. Okay, and so now, as a setting up, it seems far away, but now let's look at that a little closer. 0 to the 3rd power is a 0, and that term here is also going to go to a 0. That is a 0 as well. So all of a sudden we have left c equals 3. So this is the usefulness right here. Now we have found for ourselves, after all that work right here, now we have found for ourselves and allowed me to swing back on the other board and use that little space right here. So now we have come to, so it leads to, I'm using this big arrow head right here, this leads to, we've come to capital F of x. That function we have found here is 1/3 x cubed plus 3/2 x squared minus 5x, but now plus 3. Plus 3. All right. So this answer here is the answer that satisfied being a capital F of x, but when x equals 0, f of 0, capital F of 0 equals 3. Okay. So really the work here, a lot of times many instructors, including me, refer to as the step where we solve for the value of c right there. Okay, and so now before I'm completely, and that's how we're done with this problem. But before we are completely finished with this problem, before we solved for the c value, then this was called a general antiderivative. Okay, and so now, but now when we came to this particular member of the entire antiderivative family here, then I refer to this one here, this answer that we put in the box right here. This is now this is called a particular antiderivative. Okay, a particular antiderivative, and that's what it is, because this is the particular member that satisfies the requirements here. Satisfies the requirements that, hey, capital F at 0 must equal 3. This is a requirement. Okay, but now anyone viewing this video could be on the same kind of problem here, but anyone viewing this video can be heading into a different career path later. So some students, some calculus students viewing this video to prepare yourself to go into engineering field, physics field, or the chemistry, or those fields where it's heavily related with math, where the same problem here, but some viewers might be, after this course, after this lesson, after this course in calculus, we'll end up in business field or health science field, things like that, where you don't have to have that much requirement. So allow me to bring up another term right here, which is more heavily more heavily related to the students who are going for engineering field or physics field, because you will end up with a course later in your learning progress that comes back to this kind of problem a lot. So this particular comment I'm about to make here, this particular remark I'm about to make here, is particularly for students, for calculus students, but who are on track to engineering or physics majors right here. So this overall problem, from the beginning, we have a given function, and we're trying to find an antiderivative that satisfies a requirement right here. And let me even clear out the solution, because we already found a solution. We already had the solutions here. I just need viewers to pay close attention to this. And again, I'm explaining this with to students, to calculus students of mine who are on track to professional fields where it involves engineering work or physics work and all that. This kind of problem is being referred as an initial value problem. It's a problem to solve, but the whole problem here is called an initial value problem. And this particular requirement here that I'm putting in the box is called the initial condition. And calculus students who are outside of the engineering field or physics field can still learn from this. It's not a hard concept to learn, and I'm pretty sure somewhere here and there you will run into a problem that relates with this as well. So this whole problem from beginning to the end we've done is called initial value problem, and this particular line right here is called the initial condition. Okay, and then part of our work, I've been calling these the general antiderivative, and this is the particular antiderivative. But in the end, general antiderivative or particular antiderivative, any of these two is a solution to a problem. We had a problem, and then any of these is a solution. And so you will hear a lot of times the term as following. See, this antiderivative with the constant c, the general antiderivative, is regarded as let me find a good space to write that. This answer right here is called, this is a general solution. Okay, so you found a general solution, which is just nothing but just the general antiderivative of your beginning of your initial value problem. And then this final answer right here is called the particular solution. Particular. All right, particular solution. All right, so that's as I said again, that. It seems like I'm making this remark here specifically for the calculus students who are on track to professional careers with engineering or physics major or anything like that. But anyone outside of those fields are more than welcome to understand this, because I believe it's easy and easy enough to understand. Okay, and it will have some applications. Okay, so. All right, so now let's put up a summary here, as we are getting near the end of our lecture here, as we're getting closer to ending our lecture. All right, so I've been showing the use of the symbols for antiderivative, but so now let me make a formal chart right here. So now when we have our function being a special function, x to the n. So when we're in that class of a power function, okay. When we're in that class of a power function, then the function would appear as just simply x to the n. Then we have learned this rule over here. So finding the antiderivative on the power function x to the n simply is going to give us the answer as 1 over n plus 1 times x to the n plus 1. But then this rule, that's why it's called a power rule, because it works on a power function. It only valid for n anywhere other than -1. Okay, so original function is in x to the n. Taking the antiderivative will land us into the 1 over n plus 1 times x to the n plus 1. That's the first rule that I've introduced a little while ago. Okay, and it should be well familiar with anyone at this time of the lecture now. And then we advance further to another special one that I wouldn't even know what to call that one, but that function 1 over x right there is special enough that when we take the antiderivative, right, then it lands directly into natural log of absolute value x plus the constant c. And this is that function where it compensates, that it's filling in the missing hole for what happens when n equals 1. Because, I mean, what happens when n equals -1? Because, see, 1 over x is the same as the power function x to the -1 power. But we don't treat it as a power rule. We don't use the power rule to find the antiderivative there. We use the logarithm rule right there. And so now, before I move on to the next one, the next family of function in our chart here, you see, I have to point out that. Let me quickly navigate to my other board right there. All right, so every comment I'm trying to deliver here throughout my lessons came out from real experience I've had back in the times. In the times where I'm teaching face-to-face courses. So, of course, the antiderivative of 1 over x is natural log of absolute value x. No doubt about it. Okay, but at this point, you gotta take my words for clear. I have not taught, because that will have to wait for much later videos when your skill in taking antiderivative has developed much further. Here we just take anything that we can clearly see the reverse way. So in other words, what I'm really trying to say now is that I keep having students mistakenly antiderivative of natural log of x equals 1 over x plus c. I am sorry to say this. This is incorrect. You see, if we look closely, antiderivative of 1 over x will equal the natural log of x, natural log of absolute value x plus c. But this we have not learned yet, so this is not the answer. In some of my video lecture, which is if this is being placed in a formal calculus course, it's going to come in much later. Usually, throughout at about the middle of a calculus quarter right there. I mean, a calculus 2 quarter where it's heavily teaching about doing this antiderivative work. Okay, so this is not the answer to antiderivative of natural log of x. So for now, at this point, when I'm trying to make this summary chart right here, which is only including the very basic one, there are no rule for there are no rule for logarithms right now. We don't have any rules for that. So we're gonna have to leave that out, because you see power function, and this is starting to bring us into that family that deals with log. So people might think that I'm gonna start writing down what's the antiderivative for a logarithm. We won't have a direct rule for that for now. So I'm gonna leave logarithms out on this chart right here. So the next function that we're looking at is exponential function. Okay, so exponential function. And again, I'm only going to focus on the very basic one that we have seen through the earlier part of the videos, of this video lesson here. So that e to the x. So when we take the antiderivative of e to the x, it gives us just that e to the x again, plus c. Okay, and again, I'm going to swing back to my other board and mention another remark here. So I would like to point this out as a special exponential function antiderivative, but you will learn how that became true in the later part of our learning. But for now, we're just going to take that as a little special rule as well. Okay, so anytime that you are taking the antiderivative of e to the x, yes, needless to say, the answer is e to the x plus c. That's easy. It came. I wrote it on the other chart, on that chart on the other board. But now, this is a little bit of difference here. Anytime we're taking antiderivative of e to the ax, how's that? Where a here is just a coefficient together with the x in our exponential part, like that. Then the answer here is actually like this. It's repeating e to the ax. Yes, it has a plus c, an overall constant there, but it needs to multiply as a coefficient 1 over a here. For now, again, I'm asking any viewer or any student of mine who views this video lesson, take this as a simple special case. Because immediately, usually right after this lecture, I usually push that into a few different examples. So showing you this as for now as a preview right here will give you a good understanding and have some fascinating time with seeing through my examples, which I deliver later. But for now, again, of course, I have not proven how this is true yet. But you can take that as a rule for now, as a little rule. Okay. So as a quick example, if we're taking the antiderivative of e to a, how about 0.1x, okay? Functions like that exist out there. So e to the 0.1x, if we want to take that antiderivative, then our answer would be e to the 0.1x, okay, with times 1 over 0.1 in front, okay? And that gives us here, that plus c. That's how it happens, and that's only a quick little illustrating example. And so now I can, after all that explanation, and I hope you can take it in that simple direction, then as a subfamily, as an extra, or as a little advanced version of among the exponential functions, then we have another one. So antiderivative of e to the ax. that will give me 1 over a times e to the ax plus c. Okay, and so